and Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello students, so welcome back to the continuing session of the ray optics. So last session we learned about the dispersion, correct? So today we are going to learn about some natural and some fascinating phenomenon. So what you can see on the screen, yes, it's in rainbow, a beautiful rainbow, isn't it? So let's see how has it been formed, and the physics will answer to your all the questions. So a rainbow is formed when the ray of light strikes a raindrop. There are three things are happening. There is a dispersion, refraction and the total internal reflection. Now to see a rainbow, the sun has to be behind the observer. So over here you can see I have the spherical raindrop. There is a sunlight. Over here we are having the refraction and the dispersion. The light is splits up into the 7 colors, 7 beautiful colors, and when it strikes the inner surface, it is totally reflected. Again we have the refraction at this point because it is moving on from the denser to the rarer, and finally when it comes out, the violet light is subtended with an angle of 40 degrees and the red with an angle of 42 degrees with the incoming ray, and the remaining colors falls in between this. So this is how a rainbow is formed. Now we have got two types, we have got primary and the secondary. So let us go for the primary rainbow. So here it is a process wherein we have got the two raindrop. So the ray is incident, it suffers the refraction, total internal reflection, and then the splitting of the colors, that is the violet and the red. From the second, same procedure is happening. So here we have the splitting of the colors and the observer sees the red on top and the violet below. So when he sees this pattern, it's the primary rainbow which has been formed. Again it has got the 3 steps. We have the refraction, total internal reflection and refraction back. So it is a combined effect of 3 things. Now let us go for the secondary rainbow. Now secondary rainbow is a combined effect, of course, of the refraction, dispersion and a total internal reflection, but over here it suffers total internal reflection at 2 places. So the finally an observer sees the violet on top and red below, and the secondary rainbow is fainter than the primary, that is because it suffers 2 total internal reflection. So this is how is the formation of an rainbow. So I can show you a picture. So here you can see a primary rainbow and a secondary, wherein secondary is in fainter than the primary. Now there are some more interesting phenomenon, some interesting facts. Now what you can see, of course you can see a beautiful scene. We have got the blue sky and the white clouds. Now you have ever wondered why the sky looks blue and why the clouds are white? Yes, your physics is going to give you all these answers. When the blue, the sunlight, if I've told you, it's a combination of all the colors. When the sunlight passes to the atmosphere, it gets dispersed. The one with the lower wavelength, the color with the lower wavelength scatters more, that is because of the Rayleigh scattering law, which says amount of scattering is inversely proportional to the 4th power of the wavelength. So the one with the lower wavelength scatters the most. So, blue scatters more. Now, the question arises, the violet has a lower wavelength than the blue. Yes, correct. Violet does scatters more than the blue, but our eyes are more sensitive to the blue color, hence we see the sky as blue. Now, what is the reasoning about why the clouds are white? Now, we know that cloud has got the dust particle as the raindrop. Now, these are slightly bigger in size and they do not obey the Rayleigh scattering law. They scatter all the colors equally in all the directions. Hence, we see the clouds white. Wow, isn't it? We have the sun at the sunrise and the sunset, there is a reddish appearance of the sun, right? And why is it? During the sunrise and the sunset, the sunlight passes through a larger distance. So, the colors with the lower wavelength are already scattered. The one which is least scattered, that is the red, which reaches to the observer's eye, and hence we see the sun in red in colors. So, haven't you seen? We have got so many answers to so many different facts, isn't it? Why the sky is blue? Why there is a reddish appearance? Correct? So, it is something really beautiful. So, let us go ahead. Now, this is the last subtopic of our ray optics chapter, that is we will be learning about the optical instrument. We will be learning about the microscope, we will be learning about the telescope. Now, we have been bestowed with one optical instrument, that is our eye, isn't it? We are so lucky to have it so that we can see this beautiful world around us. So, let us first learn about the eye and then we move on to the optical instrument. So, we have the figure of eye over here. The light enters the cornea. We have got the pupil, iris, there is a ciliary muscles which is holding the lens. Here is the retina onto which the image is formed, and the image formed is interpreted by the brain, which takes the optical nerves, takes the information to the brain. Now, we need to learn about a term known as accommodation. It is about the ciliary muscles. They contract, they expand so as to have a good image on the retina by changing the focal length of the lens. So, that is done by the ciliary muscles. Now, we can see the distant object. You can see, I can see an infinite, the object which is placed at an infinite distance, like the mountains, the rivers, we can see at a big distance. Now, what about the near point? There you go. The closest distance for which the lens can focus light on the retina is called least distance of distinct vision. The closest, if I hold an object, okay, if I hold an object at 25 degree, at 25 centimeters, I can see it very clear. Closer than that, the image is going to be a blur image. So, the distance, the closest distance at which you can have a good image is termed as the least distance of distinct vision or the near point, and it is given by 25 centimeters. Okay, so normal, the standard value is 25 centimeters. In some aged people, this may increase. For the younger kids, this may decrease also. But standard value is given as 25 centimeters, wherein which gives you a correct image on the retina. Now, though we take good care of our eyes, there are some defects do come in some people. So, let us move on to the defects. There is the optical defects of the eye. First is myopia or short sightedness or near sightedness. So, what is happening over here? Can you see the image? This is an object the rays are coming, the image is formed before the retina, isn't it? We want the image to be formed on the retina. So, there is a defect, correct? Now, how to correct the defect? The rays are converging over here just before the retina. So, I need to have a diverging lens, isn't it? So, here I have placed a concave lens so that I get the image right onto the retina. Next is the hypermetropia or long sightedness or far sightedness. In this, the image instead of forming on the retina is forming behind the retina. So, this has been corrected by using a convex lens. Astigmatism, in this case, you can see the image is formed on the retina, but how is the image? Image is distorted. A person suffering from this defect cannot focus on the horizontal and vertical lines simultaneously. If he sees a wire mesh, he sees it very distorted. Either one is perfect, the vertical or the horizontal. So, how this has been corrected? This is corrected by using a cylindrical lens. So, use a cylindrical lens and image will be clear. So, that is the defect which can be corrected. Next is phobia, which arises due to aging, and that is corrected by the converging lens. So, these were the defects which occurs in the eye. So, let us go ahead. Now, we are going to learn about the optical instrument as I have told you all. Now, listen carefully to the first one. We will be learning about the microscope, then we will shift on to the compound microscope and then to the telescope. So, you listen carefully to the first one because next two are really easy if you understand this one. So, let us move on. Now, what do I have over here? Check out the figure. So, over here you can see the eye, you can see our eye, a beautiful eye, and there is an object which has been kept, and there is an angle subtended by the object, and the object has been kept at the least distance of distinct vision. So, how you can visualize it? Say suppose I am holding the object, that is my eyes, it is making an angle at the base and it will make an angle at the top. So, there is an angle which has been subtended. Now, I want to know about the magnification, yes, the magnifying power. Hence, I have kept the object at D. Why? Because if I keep it away from the D, isn't it that your angle is going to go, it is going to decrease, and I cannot keep lesser than D. Why? Lesser than D, the image is going to be blur. I am not interested in the blur image, but I wanted a clear image. So, I have kept the object at D is the height h. So, what do I get? The theta as opposite upon the adjacent, that is the h by D. So, I can take the tan of the theta. So, theta at the object. Okay. Now, going ahead, now what I have done? Over here, I just looked at my object just by the naked eyes. Now, I have placed a lens. Why? That is because I need magnification, isn't it? A simple microscope wherein you need a magnification. So, here I have placed the lens, okay, and the eye has been focused at the infinity. The object has been kept at the focus, and this is the focal length. So, image definitely is somewhere at the infinite positions. So, this is my theta I, that is the theta image. Now, the lens which has been used is of the very short focal length, so much so that it is less than even D. So, for our microscope we are using a lens with a very short focal length. Now, this is also termed as the normal adjustment, that is when the ciliary muscles are relaxed, no straining of it. That is the normal adjustment where you can see the image without any strain. Okay. So, what is the theta I over here? Theta I is going to be h upon f. Again I have taken tan of theta. So, h upon f. I am interested in the magnification, correct. So, magnification is given as angle at the image to the angle at the object. So, take these two equations, cancel out, and this is what we get, that is m is d upon f. Have I got the magnification? Yes? Check out, yes. That is because look at the denominator, we have the f, and I told you it is of the short focal length. So, shorter the focal length, definitely high is going to be the magnification. Okay, so I have achieved the magnification when the image is at the infinity. Is that clear? So, let us move on to the next. Now, let us check out when the image is formed at the least distance of distinct vision. That is my aim, isn't it? I want to get it at the least distance. So, here is your ray diagram. So, the observer that we, when we are using the microscope, we are at the lens. So, eye is focused on the near point. I am interested in getting the image at the near point. So, that was my object. So, the rays are coming over here. This object I have moved little closer to the lens. Initially, I told you it was kept on the focus. So, the image was at the infinity. Now, slightly closer, and we know that when it is in between focus and the optical center, we get a virtual image. Okay, we get a virtual image which is enlarged and on the same side, and it is at the erect. So, we know this, it is defined as the ratio of the angle subtended by the image to the object when both are at the least distance of distinct vision. So, going in the same way, we get theta I upon theta naught as these two equations which I have just grabbed one from the previous one, cancel out h, and what you get is magnification as d upon u. Okay, so, this is image formed at the least distance of the distinct vision. I have just taken the same thing, I have written it over here. Now, this magnification I want in terms of the focal length. So, let me use the lens formula which is 1 upon f equals to 1 upon v minus 1 up by u. Rearrange it, you just get 1 by u on this side, then it becomes 1 by f. Use the sign convention. We know image is formed at the least distance of distinct vision, so it is minus v, u minus u. Substitute this, you can divide it by d. Sorry, you have multiplied over here by d, so the dd get cancelled, and what ultimately remains is this. So, d upon u is 1 plus d by f, and we know that d upon u is nothing but the magnification. So, magnification in terms of the focal length that we have got is 1 plus d upon f. So, this is the magnification when the image is formed at the least distance of distinct vision. So, this was about the microscope, when the image is formed at the infinity and when the image is formed at the least distance of distinct vision. So, now let us move on to the compound microscope. If in case you have followed this, compound microscope will be very simple. Now, that is your ray diagram. Now, simple microscope, you know, we just use a one simple convex lens, and we have got a certain magnification, and let me tell you, the magnification was a reciprocal with regards to the focal length, and in microscope we use a short focal length, but there is a practical limits how short you can use it to increase your magnification. So, instead of that, we move on to the compound microscope, and we choose two lenses, one which is termed as the objective, one the next one is the eyepiece, and this eyepiece works exactly like the simple microscope. So, what the objective does, we have the object in front of the objective which forms an image It's in real inverted and slightly enlarged. So, this enlarged image is acting as an object for the eyepiece and the final image is highly enlarged. Isn't it? We want a highly enlarged image. So, this is the ray diagram for the compound microscope. So, let us move for the derivation. So, magnification due to objective is given as L upon F naught. L is the tube length, MO stands for the magnification by the objective. See, objective is the lens close to the object, eyepiece is the lens close to the eye, which you check out. Okay. So, this is the magnification by the objective. Now, when the final image is formed at the near point, ME, that is magnification at the eyepiece, you get as 1 plus D upon FE. Now, this I have completely taken up from the simple microscope equation, that is when it is formed at the near point. E is your eyepiece. This is when the final image is formed at the infinity, we know ME will be given by D upon FE. So, the total magnification when the image is formed at the infinite position is going to be the product of magnification at the objective and the magnification at the eyepiece, that is L upon F naught into D upon Fe. So, you can check out, students, this is what is the magnification by the compound microscope when the image is formed at the infinity. L stands for the tube length. So, this was about the compound microscope. Moving on to the next, that is the telescope. So, that is your ray diagram. You can see clearly the objective has the bigger size than the eyepiece. That is, the rays are coming from the distant object. Telescope basically used to check out the celestial objects, the objects which are far away, that is the stars, the planets. So, the rays are coming from far objects. We have the observer over here and finally, we get the image. So, the magnification is given as F naught upon Fe, that is F objective, F eyepiece. Now, refracting telescope is used for terrestrial as well as the astronomical observation. Now, the main consideration when we are using a telescope, main thing we want is a high light gathering power and high resolutions, correct. Now, in order to have a light gathering power, the objective size has to be more bigger, the aperture has to be more. So, the largest lens is of the diameter of 1 meter and which is in USA. Definitely, can you imagine the bigger size? But this comes with a certain disadvantage. Such a big telescope becomes really very heavy, bulky for the support. So, we have the another type which is known as the reflecting telescope. There are many advantages. We have the mirrors used in it. So, instead of lens we use the mirrors, and the advantages is there is no chromatic aberration, there is no spherical aberration, they are free from it. The only problem it has that it focuses the light inside the telescope tube. So, the observer need to sit inside, the viewer has to sit inside the small cage. Okay, students, the same problem can be resolved by having another mirror, and this type of telescope is termed as the Cassegrain telescope, wherein we have the two mirrors in it. Now, the largest telescope in India is of 2.34 meters and that is in Tamil Nadu, and in world the largest one is in USA with a 10 meters in diameter. So, you can imagine it is going to be a huge telescope. So this is what we learn about the optical instrument. So we are at the end of the chapter, so let's revise. So what we did in this particular chapter, we learned about the reflection, refraction, total internal reflection, the beautiful phenomenon occurring in the nature. We learned about the lenses, prism and the optical instrument. So hoping you all have followed it. So thank you students, thank you very much. Do keep studying.
Prudent Scholars, powered by Lupin Pharmaceuticals.
अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस। अब आपकी सुरक्षा आपके हाथों में। ल्यूपी सेफ हैंड सैनिटाइजर, आपका और चेन्नई सुपर किंग्स का फर्स्ट लाइन ऑफ डिफेंस।